Alright, Assalamu alaikum. So in this video, we'll be starting off and hopefully, we'll be starting off with electrolysis using active electrodes. So far, whatever we have studied, including electrolysis of molten compounds or aqueous ionic compounds, it was all done using inert electrodes. This time, we will be moving on to active electrodes and see how the reactions differ. Now, before we jump into this topic, let's take a small review of what electrodes exactly are, their purposes, and the parameters of their classification. We have done this time and again, but we'll just do this again for one last time, hopefully, and that will hopefully help us in understanding the topic better. So, an electrode basically is a rod that ensures the connection, the electrical connection of the electrolyte with the power supply. So an electrode basically is a connection of the electrolyte with the power supply. And it serves another very important purpose, that is, it ensures a directionality in the flow of current, and hence it helps move it gives the cations and the anions in the solution or the molten compound a direction, and this ensures and this helps the cations to migrate to one side and the anions to migrate to the other side, and hence ensure the segregation and breakdown of the ionic compound. So each electrode with its distinct charge, with its different rather, with its different charge helps the cations and anions to be separated from one another. Now coming to the classification. In the first video we studied that electrodes can be classified on the basis of two parameters. The first parameter was the reaction that takes place at each of the electrodes. And the second parameter was the material with which the electrode is made. Now, based on the first parameter, we had called the electrodes as the cathode and the anode. We have the cathode and the anode. The cathode was the electrode at which reduction takes place, and anode was the electrode at which oxidation takes place. Whereas when we come to the material with which the electrodes are made, we had two classifications, and that is the electrode was either called an inert electrode or it was called an active electrode. And inert electrodes do not take part in the reaction themselves. Do not take part in the reaction. Whereas active electrodes do take part in the reaction themselves. And why is that so? It's basically because of the material with which the electrode is made. So when will an electrode be called an active electrode? Let's take an example. Let's say that I have an electrolyte which is a solution of copper sulfate, and I dip a copper rod In fact, I'll just dip 2 copper rods into it and make it a complete electrolytic cell. Here's this mess. Right, so both of these are copper rods, and I've connected them to a power supply. Right, so these copper electrodes, when they are dipped into a solution of copper sulfate, will be called active electrodes. These are active electrodes. So let's write something about active electrodes. Here we go. When the electrode is made of the parent metal, of the solution being electrolyzed, the electrode is referred to as an active electrode. Right. Let's understand what I've just written. See, and we'll see this diagram as well. Alright, what I'll do is I'll just try to shift this diagram to some other place in our canvas. Okay, so it's messing up now. This sometimes does mess up. Right, let's bring it here. Fine. Perfect. So now I told that these electrodes, these copper electrodes, are active electrodes basically. Why? Now let's take a look at this definition that I've just written here. An active electrode is an electrode which is made of the metal whose salt is being electrolyzed. So why are we referring to these electrodes as active electrodes? Because these are made of copper, and copper is basically the parent metal of copper sulfate. That means that if, let's say, I have a solution of iron sulfate and I dip the same copper electrodes into this solution of iron sulfate, these will be referred as inert electrodes. Why? Because the electrodes being used to electrolyze the iron sulfate solution are not made of the parent metal of the salt. However, if I had used iron electrodes here instead of copper electrodes, these would have been referred to as active electrodes. Likewise, if I replaced copper here with iron, these electrodes again would be inert electrodes and not active electrodes. Why? Because iron is not the parent metal of copper sulfate. So what makes it so special that that we are studying it separately, and as we will see, the reactions that take place will be completely different from what we observe in inert electrodes. So before that, let's try to understand something. In fact, this is basically a very important concept, and if you understand this right now, it will be extremely helpful for you even in A2. So let's see now. Let's see what happens if I dip a copper rod into an aqueous solution of copper sulfate. Right, so here is my copper rod and here is an aqueous solution of copper sulfate. So what is the copper rod made of? The copper rod is made up of copper atoms. So we have copper atoms here. And so I'll just write Cu, Cu, Cu. And in the solution, we have copper ions and sulfate ions as well. We are not concerned with the sulfate ions right now, so I'll just leave that. Right. Now, when we dip a metal in a salt solution of its own salt, in this case, copper in a solution of copper sulfate, in this case, iron in a solution of iron sulfate. So, once again, when we dip a metal into its own salt solution, some very interesting things happen. What happens is that here, let's take a look at this copper atom. What will this copper atom do? This copper atom will form ions. It will become an ion and move into the solution. So what happens is that copper becomes an ion. And in order to become copper ions, it needs to lose electrons. It would have lost 2 electrons to become a copper ion. So now this copper metal atom has become an ion and moved into the solution. Now what about these electrons? Electrons cannot jump into the solution. So the only place where electrons can be is the surface of the metal. So these electrons, let's say this copper ion atom has also moved here, and we have another copper ion. So we have electrons. The electrons released stay on the surface of the metal. So far what we have just studied, we'll write this down here. When a metal is dipped into its own salt solution, what did we just observe? The atoms of that metal lose electrons to form ions, right? And what happens? To form ions and move into the solution. The electrons lost stay on the surface of the metal. And why do this stay on the surface of the metal? Because they cannot move into the liquid and they don't have any other place to go. Now something really interesting happens. Now if you take a look at this metal rod here, this metal surface is basically in constant contact with the copper ions in this solution. So what happens is that these copper ions move towards this rod and gain the electrons present on the surface of the metal to form copper atoms. So on the one hand, what was happening was that copper atoms in the rod lost electrons, formed ions and came to the solution. But on the other end, what happens is that copper ions in the solution move towards the rod and gain the electrons lost by the atoms in the copper rod and form copper atoms themselves. So on this end, what's happening is that copper ions gain the electrons and form copper. So let's write this part down that we just studied. On the other hand, the rod with the electrons is in contact with the positive metal ions in the solution. As these positive ions move towards the rod, they gain the electrons present on the surface of the rod to form metal atoms. Yeah, that's it. So all in all, in this apparatus that we just drew, this apparatus, there is no net change in the structure of the rod. Why? Because if copper atoms are being lost as copper ions, then copper ions are becoming copper atoms and replacing these lost atoms. Copper ions are becoming copper atoms and replacing the atoms that were present initially in the rod and were lost in the solution. So there's no net change here. No net change. However, if somehow we can provide an outlet for these electrons, this thing, that means this no net change situation won't develop. Why? Because the electrons would then be able to go somewhere else. Here's, let's write E here. And therefore, there would be no electrons available on the surface of the metal to bind with the copper ions approaching the metal surface. So that's exactly what happens when we electrolyze a solution using active electrodes. And what's an active electrode? Let's return to the definition once again. When an electrode is made of the parent metal of the solution being electrolyzed, the electrode is referred to as an active electrode. For example, copper being used to electrolyze copper sulfate, or iron being used to electrolyze iron sulfate or iron chloride or whatever. And I just explained the mechanism. Let's very quickly review this again. That what when we dip a metal into its own salt solution, the metal atoms in that rod lose electrons, form ions, and move into the solution. So we can add the state symbols to this equation that this copper was a solid. Why? Because it came from the rod. It lost electrons, formed ions, and moved into the solution. But on the other hand, what happened was that copper ions in this solution gained electrons which had actually stayed on the surface of the metal while the copper atoms of the rod were forming ions. They stayed on the surface of the rod to combine with the copper ions in the solution and formed copper. So there was no net change. However, if we provide, as I just said, and I'll write this down here, in this whole process, there is no net change. However, if we provide an outlet for the electrons being produced, and where are the electrons being produced? Here, in this part of the reaction, electrons are being produced. However, if we provide an outlet for the electrons being produced as the metal atoms formed ions, no electrons would be available on the surface of the metal rod to combine with the ions in the solution. And this is the basis of electrolysis using active electrodes. So now let's see. Right. So I have, let's say, iron sulfate, and I'm electrolyzing it using iron electrodes. So this is an iron electrode. Here's my cell. Right. And these are my electrodes. This is the negative electrode, so this would be the cathode. And here is our positive electrode, which is the anode. Now let's go back to these equations here. And there's one small thing that I think I should have told here. What kind of reaction is this? We can see that electrons are being lost. Therefore, this is an oxidation reaction. Here, electrons are being gained. Therefore, this is a reduction reaction. Now remember, this is not an electrolytic cell. This is not an electrolytic cell. Why? Because there's no battery, there's just one rod being dipped into this solution, and obviously, because it's not connected to any power supply, it cannot be an electrode. It's a simple rod, nothing else. So this is not an electrolytic cell. But this is an electrolytic cell. Now we know that oxidation occurs at the anode and reduction occurs at the cathode. This means that the reaction in which electrons will be lost will be happening at this electrode, and the reaction in which electrons are gained will occur at this electrode. So what will be the procedure? Now let's see. Here we have iron atoms in which make up this rod, and in the solution we have iron ions. So we have, let's okay, here we have iron atoms here, and we have iron ions in the solution. Now what happens is that these iron atoms in the metal rod will lose electrons and move into the solution as iron ions. As a result, what happens is that electrons are produced. But this time, electrons will not stay on the surface of the metal. Why? Because this time, because of the presence of an external circuit, they have a route of outflow. Therefore, the electrons will now move to the cathode. So, what happens is, let's write this down again. So, at the anode, the iron atoms lose electrons to form ions. These ions move into the solution. The electrons produced do not stay on the surface of the metal, but move to the cathode via the external circuit. So what will be the anodic equation? The anodic equation is that iron from the electrode moves into the solution as iron ions and loses 2 electrons in the process. So solid and aqueous. So you can see that this electrode is basically taking part in the reaction itself. Why? Because it's dissolving in the solution and giving us more and more iron ions. Right. What happens at the other end of the cell? I told you that electrons are moving in the external circuit and they travel to the cathode. Here they come at the cathode. At the cathode, what happens is a reduction reaction has to take place. So these iron ions move to the cathode where they come in contact with these electrons and they gain the electrons to form to form iron atoms. So what happens at the cathode? The electrons move to the cathode and come in contact with the iron iron ions, with the iron ions. These iron ions gain the electrons and form iron atoms. So what happens is that Fe2 plus ions gain the electrons and they form Fe. So as a result, what will happen is that with time, iron will start forming at the cathode. As more and more iron ions move to the cathode, there will be more and more iron depositing at the cathode, and therefore the cathode becomes larger. Cathode becomes larger. Whereas what will be happening at the anode? More and more of the anode will be dissolving as the ions, as the atoms at the anode become ions and move in the solution. Therefore, the anode diminishes. So the observations of this reaction would be: observation number 1, cathode larger. And this really helps me to remember the principal reaction of the of electrolysis using active electrodes. I tell my students that the rule of electrolysis using active electrodes is the Champions League. I'm a football fan, so this is the second football reference that I have given in my videos of electrolysis and electrochemistry. So the rule is Champions League, CL, cathode larger. And why does the cathode become larger? Because the anode becomes smaller. Anode diminishes. In other words, what you can say that the iron atoms that were lost at the anode are actually gained at the cathode. Therefore, there is no change in the electrolyte. So we know that FeSO4 is basically a green colored solution. So the third observation would be that the color of the solution and the concentration of the solution remains unchanged. Electrolyte unchanged. That's all for electrolysis using active electrodes. Now let's review everything again. The first thing that I told you was that when we dip a metal into its own salt solution, two reactions basically take place. This is the first reaction. What happened was that we dipped a copper rod into a solution of copper sulfate. The copper rod was made of copper atoms. When it came in contact with its ions, it itself, the atoms in the rod, they formed ions themselves and they moved in the solution. And as a result of this, electrons were released. And these electrons deposited themselves on the surface of the metal. Now, and this is shown by this first equation here. Now these electrons themselves can't jump into the solution. Instead, they stay stuck on the surface of the rod. Here, this rod with the electrons stuck onto them come in contact with the copper ions present in the solution. These copper ions move towards the rod and combine with the electrons which were produced by the atoms in the copper rod forming ions. And as these ions gain these electrons, they form the metal itself, and hence there is no net change. But if we can somehow provide an outlet for these electrons which were produced here, then there definitely would be a change. And how would this change be produced? How can we ensure an outlet for these electrons? That is done by connecting it to an external circuit, as we did here. We were electrolyzing iron sulfate using iron electrodes. And what we did was we put a battery, we connected it with wires, provided a complete circuit, and now let's see what happens. What happened was that at the anode, which is the electrode at which oxidation takes place, what happened was that the iron atoms that made the electrode, they lost electrons. Iron in the rod formed iron ions, and those iron ions moved into the solution. Now, the electrons produced, they have an outlet. Where's the outlet? They move up the electrode into the external circuit and they come to the cathode. And they are stuck to the surface of the cathode. At the cathode, the iron ions in the solution move to the cathode, where they gain the electrons which had arrived from the anode and form iron metal. So on the anodic side of the reaction of the electrolytic cell, more and more iron atoms form ions and move into the solution. Hence, the anode diminishes. Whereas at the cathodic end of the reaction of the electrolytic cell, more and more iron ions move and gain electrons, forming iron at the cathode, and therefore the cathode becomes larger. And on the basis of this, we came to our observations. The first observation being that the cathode is becoming larger. And I told you about Champions League. That this is basically a very nice way to remember what happens in electrolysis using active electrodes. That is Champions League. The cathode becomes larger. And why does the cathode become larger? Because the anode is becoming smaller. In other words, we can say that the source of iron metal being formed at the cathode is actually the anode. And as a result of this, we come to our third observation, and that is the electrolyte remains unchanged. And therefore, the color of the solution and the concentration of the solution, they all remain unchanged. Now, this might seem, so what happens at the cathode? Cathodic equation. Oh, alright, here's the cathodic equation. I've written it already. So here is the cathodic equation. Now, if we construct the overall equation for this reaction, it will be something like Fe solid. In fact, there would be no net reaction. Just take a look here. This is the anodic equation. Fe gives us Fe2 plus 2E minus. And here we have Fe2 plus 2E minus gives us Fe. Things on opposite sides can be cancelled. So this can be cancelled, this can be cancelled, this can be cancelled. There is no net reaction taking place in the electrolyte. Remember, these equations basically tell us about the situation of the electrolyte. So because everything cancels out, we come to the conclusion that there is no net reaction in the electrolyte. Now, this may seem extremely insignificant and frivolous, but this actually has a lot of importance. And in the next video, we'll be studying the applications of electrolysis using active electrodes. If that's all for this video, if you have any confusion in understanding the concept behind electrolysis using active electrodes, please comment in the comment section and I'll try to come back to you in another video, or I'll respond to you privately. With that, we are done with this video. Assalamu alaikum warahmatullahi wabarakatuh. We'll meet in the next video with applications of electrolysis using active